Here I want to make conclusions and make a final remarks of what we have learned from this chapter, the pure bending. And also this section will contain some self exercise examples. And in this video lectures, I won't go over the self and the exercise examples, but those examples will be in the handouts I give to students which take the online class with me. So basically for pure bending, that is what we've seen, and we say from the very beginning, what we started is we have a pair of the bending, and for example here applied in the symmetric plane, and for this example is curve up, okay, and to curve up, then so far we've been emphasized is on one side of the cross section, but here let's bring kind of the zoom out our viewpoint to see the whole free body diagram, and here I want to see what is the distribution on the two sides. Basically you should expect, because this is the pure bending, so the distribution of the stress, the bending stress, should be symmetric, should be the same on the sides. That means the top portion is in compression, and the lower portion is in tension. And in terms of the magnitude, and if you pick at if you pick a point with the same value of the y, then the magnitude should be the same. Okay, just showing like this. So this is the viewpoint. I simply kind of straight the curve beam and then have a better view. Okay, have a better view of the things. So again, you pick different, whatever the cross section you pick, then that distribution should be looking like this for a bending like this one. So that is what we learned. And furthermore, you should be able to this point, in terms of the quantification, you should know how to calculate the bending stress, and which is the my over I. Okay, the magnitude my over I. M is a given bending. Y, for example, if you want to calculate the point here, then you simply measure the distance from here to the neutral surface. Okay, so that's a Y. I is a moment of inertia of the cross section about the neutral axis. So if you look at from, say, if you are a small guy sitting on this axis, looking from this viewpoint, and for example, if this is a cross section you see, okay, so intersection of the neutral surface to the cross section, and that gives us the neutral axis. So that is the definition of the neutral axis. So the moment of inertia is respect to the neutral axis of this cross section. And again, here previous sections we have one section dedicated to the review and the calculation of the I. Okay, go there if you don't still not clear how to do it correctly. And so here I want to continue the further to explore the concept here. So for example, let me pick a free body diagram. The free body diagram basically is in between the two sections, and also the free body diagram, the bottom side of the free body diagram is somewhere here. Okay, so let me isolate the selected free body diagram like this. Basically the free body diagram is ranging from y1 to y2, from here to here. Okay, and in terms of these selections, I want to see what's going on in terms of reactions in this free body diagram here. So here choose this free body diagram, sorry. The top side is the top edge, that is a free surface, and here we only have three sections, this and the bottom one that has been selected from this free body diagram. So now we simply looking into what is the distribution of reaction in the three cross sections that been picking up. On this side, this is a cross section. This cross section basically we know that they have the constitute of the bending stress, and like this wedge shown here. So the normal stress to this surface basically is the area integral of those bending stress. And here, let me put into this formula here and symbolic, okay, the bending stress sigma x, I do the surface, the area integral from y1 to y2, and that is f2 here, and totally is in that direction. Similarly, and that is the reaction on this side, okay. So here, let me ask you, in terms of the magnitude, is F1 does F1 have the same magnitude as that of F2? In terms of magnitude, is F1 equal to F2? And give you a few seconds to answer this. Again, you start from here and start from our previous one. I said that the magnitude of this stress and should be the same on the both sides. So continuing from that point, then you should right away to tell me the F1 in magnitude equal to F2. Okay, so you must have this one confidently answered, and otherwise you need to go back our previous slides and to ask yourself, hey, how do I calculate the magnitude of the stress? Okay. So now we look at the furthermore, and now we have the result, the reaction in terms of the force on the two sides. Now if we take the equilibrium in y directions, in x direction, this is my x directions and y direction here, okay. And so now we take the equilibrium in the x direction in horizontal directions, then you can see because the two forces are equal in magnitude, basically they shouldn't have any reactions at the bottom side. So the delta H is the reaction, horizontal reaction here, they must be equal to 0. Okay, this must be equal to 0 because we realize for pure bending, the force, the stress basically on the two sides is symmetric. They are basically opposite to each other, and they basically cancel to each other in terms of this equilibrium equation here. Okay, so that is what we can deduce from what we have learned from the pure bending. Keep this in mind, and in the next slide, I'm going to get one step further, and this will be the deduction. And that is where the creative, the scientific work been moving forward. Okay, so look at this. So if we consider, say, this case, this is called the cantilever beam, and cantilever beam is under the point loading here. Okay, so from here you should be, let me take a free body diagram of this portion here, and let me get that free body diagram like this one here. So again, on this side, when we take the free body diagram, this side we should expect the M2, there's a bending. The bending should be equal to, let me say the distance here to here is D1. So D2. So M2 should be equal to F times D2. You can verify that one. Again, let me call this distance is D1. Then you should be able to identify calculate the M1 equal to F times D1. Again, this is a very simple calculation from your statics. So now on this side, we have a moment Fd2. So again, we have the bending stress, and using the same concept, the bending stress is like this. And here the moment is M2. Similarly, and here the moment is the M1 here. Okay. So again, let me repeat the previous page. I picked this cross section, the free body diagram, and the same strategy. I picked this free body diagram to come to here, and this is a free surface, and that we are not so concerned. Here we're going to determine what is the reaction on this side. Sorry, and this side and this side. Okay. So repeating the similar process here, on this side, the horizontal force, and that is basically is the surface integral of this bending stress. Let me use the color here again, and So basically in this portion, the bending stress is like here, I simply copy from here, okay? So I simply copy that information to here. So we do the surface integral of the bending stress, and this bending stress basically equal to M2 and Y over I, okay, that's a compressive, so I drop the sign here. So that's integrating from Y2, from Y1 to Y2 here, okay? In the similar way, and I determine the force on the other side. Let me copy that one here. So that is a bending stress. So again, for this one, I do the surface integral. Again, this one, the bending stress is M1 times Y over I, okay? And from here, you can see the F1, let me ask you the questions. And F1 in magnitude equal to F2 for this case? Definitely, the answer should be no, because by simply looking at the graph here, I illustrated here, and for this particular example, the F1 in magnitude should be greater than F2, okay? Because here the M1 and M2, M1 and M2 is produced from here, and M1 is greater than M2. So basically F1 greater than F2. Okay, now come to the very interesting point. Now again, we take the force equilibrium in x directions. So since F1 equal to greater than F2, so they must exist direction at the bottom side to get this one in balance. Okay, so that one, the edge, delta H should be greater than 0. That is pointing to that direction. Okay. So here, at the bottom side here, we conclude the delta H, they should exist the directions at the bottom side here. So along this fiber, along these sections, the reaction force pointing to that directions, and there. So from here you can see this reaction is parallel to the bottom side, to the bottom surface. So the delta H divided by the area of the bottom surface, that gives us stress. Delta H divided by whatever the bottom area surface, and let me say the bottom area surface is delta A, okay? So this one gives us the average of the shear stress. So for this case, this is not pure bending. This is the M1 and M2 not equal, so they are not pure bending. Okay, for non-pure bending case, we should expect the shear stress exist in the beam. The shear stress exists in the beam, and that is the case I want to bring it up to you. And then you might continuously ask me, how do we able to implement the calculation procedure to calculate the sigma, the tau, for different geometry, the different cross sections, and even for different loading case other than this particular example. Okay, you may continuously ask me this question, and I can tell you this contents basically I kind of make an advertisement. This will be the contents in chapter 6. Okay, so give me a time, then we will go there, and I will start from there and by review these questions here. Okay, great.